Wow. Wow. Good attendance for second day. Okay, so we're going to pick back up with a little bit more. I think we're good on Lewis dot structures. Are we good on Lewis dot structures? Do we need more Lewis dot structures? Lewis dot structure, yeah, that's pretty 100 level. We're going to talk a little bit about how we're going to be representing structures in organic chemistry, and it takes a little bit of time to get people used to how we typically do it, because as the structures get more complex, we don't have the luxury of drawing in every implicit hydrogen. So, whereas you might see something like, okay, well, is there a garbage can? Right. Nope. So here we have propyl bromide. And this is what's called a condensed structure, where the bonds aren't shown, but you get everything that is attached, and you get an order of attachment. You can see an expanded structure, which everyone's seen before, where you draw in every single bond, and sometimes you see lone pairs as well. And this is usually people's comfort zone coming out of 100 level, is seeing how everything's attached and seeing a little, well, you don't get geometry out of this, but you can imply it based on the fact that it's tetrahedral centers. In organic chemistry, we get impatient and we don't have time to draw all the structures. So what we're going to start seeing more of is stuff like this. And this is obviously faster, right? So every end is a carbon, every joint is a carbon. So we still have our 1, 2, 3 carbons. We have our non-carbon atoms specified, in this case, our bromine. And then we know the rules around hydrogens. So we can just infer that this is a CH3 because we know it's going to need 3 hydrogens to meet the octet, CH2, CH2, and the bromine doesn't have anything else required because it likes to have 1 bond and 3 lone pairs. So all these rules we talked about last class in terms of formal charges tending towards 0 in most normal structures apply here. Now, if you're breaking those rules, if all of a sudden we have this formal charge of -1 on something, like for instance, if this was a carbanion, so our carbanion is a negatively charged carbon that is carrying a lone pair, where it only has 3 bonds. This is highly reactive. Obviously, we wouldn't assume this as drawn as a carbanion if this was a carbanion, which would require some other things to be bound to it as well. We would draw that in specifically because it's something somebody wouldn't assume by looking at the structure. But this throws people. I'm going to get to your question here. What you got?
Stupid question.
No.
Is there a convention for whether or not you start on a down leg or an up leg, or is it
Nope.
a stylistic thing?
No, it's just out of convenience. Whatever it ends up, it can be like this. But it is important that you don't do this.
What? That's totally clear to me.
Right? Exactly. It's like, oh, we got some dots and a. And this convention is going to become important because if I was to flesh the structure out, let's see if I can get something a little brighter. Instead of just this, if we were to flesh this out and actually show, this is much better, all the protons with geometry. They would have these tetrahedral arrangements where you have 100 or close to 109.5 degree angles between all of the bonds. So this zigzag we're drawing in is actually indicative of these elongated tetrahedral arrangements, which is why we draw them the way we do. It's not just a zigzag. You need to be careful when you're working with these at first to make sure you're accounting for your protons, because people tend to forget that they're there when they're doing their molecular weights. If you're evaluating the molecular weight of something, you're going to have to take some time to really go through and say, okay, this one has 3, CH2, CH2. If you have a benzene ring, a cyclohexane, CH2, 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 benzene, CH1, 1, 1, 1, 1, 1, because all these carbons have 3 bonds to them. So you have to track your multiple bonds. You have to then account for all of your protons that are implicit in these structures. And as you get a little bit of practice, it's going to become automatic, and there won't be any going back after that. Anytime you have to draw out an expanded structure, oh, it's so arduous. My hand's hurting from all the drawing. Actually, your hand's going to hurt from all the drawing, even with just the lines. So it saves everyone a lot of time.
Is there a convention to how you do the H's? Does it matter if you do line or dots or triangle first or kind of thing?
Oh, good question. Let me talk about that. Some 100 level covers it, some doesn't. So anytime I draw a solid line like this, it's in plane with this surface. So for a tetrahedral structure, you can always put 2 things in plane. And then whenever I have a solid wedge, this means it's coming out of plane like this. And then the dotted wedge is going away from you at a downward angle. So it gives you an idea of this 3-dimensionality. Now, if I were to draw this alone, and I terminated it on the end of the line, you would assume that you have carbons all over the place, and this is CH3, 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 CH3. So when you're doing these expanded structures, sometimes it's important to put, if these are protons, to put them in there, or else it's going to be confusing because people are going to assume there's carbons on the end of this, because you're assuming the end of any line that isn't shown is a carbon. But this isn't locked in stone either. So I can take any tetrahedral arrangement, because these are all 109.5 degrees. I could draw this with both of these turned up, and then I could have one coming directly out this way, and then directly back into the board. I could view it from above, where I'm looking straight down at it from here, and I would have a pair of wedges because I'm looking at it from this direction, and then I would usually have to kind of shuffle off to the side to show the wedge. You don't see that one very often, but any way that makes clear sense is okay. This is the most conventional, because if I were then to have some reaction that put another link on it, I could do something like that. To just keep expanding it. When you do it in a less conventional sense, it's harder to show longer reactions. Does that help?
Yeah.
Okay, so we're going to start reviewing atomic orbitals. And then we're going to get into a little molecular orbital theory, a little hybridization, and I have a feeling we're going to be starting Chapter 2 in acids and bases before the end of class. So Last class we talked about atomic orbitals a little bit. And this is the way electrons are housed around nuclei in non-bonding scenarios, and occasionally in bonding scenarios, but not always. Because oftentimes when you have a bond, the equations which solve for orbitals can reach better lower energy solutions through hybridization. And we're going to review the hybridization in just a second. But to get there, first, remember we have S, P, D, and F orbitals. A vast majority of what we're going to be paying attention to for organic chemistry, because carbon only has a second quantum energy level, so it has a 1s, a 2s, and a 2p. So because carbon's the foundation of most of our organic chemistry, we're not going to be doing a whole lot of D and F. So this is where we're going to be spending most of our attention for all of our bonding theory in this class. And the s orbital is spherical in nature. It has a regular spherical distribution of finding the electron at any point around the nucleus. And the p orbital has these lobes along each of the three axes, which has regions of very low density inside the zone occupied by the s orbital and regions of higher density surrounding the s orbital. So I can kind of do this kind of that peripheral look at the p orbital. So what happens when orbitals combine? There's a couple different theories, and the thing with bonding theories, and this really happens to people when they take physical chemistry also, is they get so hung up on the theory that they confuse the theory with being, bless you, a picture of reality. Theories are models which give us predictability, and they may give us some insight into the truth of the way things are, but they aren't necessarily a snapshot of reality. So it's really important. That's why we can have these different theories that have different predictive value, like which one's right. Well, for any given scenario, one theory might be better than the other, and for another scenario, the second theory, which wasn't as good, might be better for predicting in there. So the best use is to apply multiple theories, see what the prediction is from multiple theories, compare your outcomes, and hopefully you have some agreement, and that reinforces your idea of what's likely to happen. So we're going to start with molecular orbital theory. Basics of molecular orbital theory. And when we get into, actually, that'll be next semester, and when we do benzenes and aromatics, and we really get into the application of molecular orbital, because that's where it really shines. But it's worthwhile here because we'll be referring to antibonding orbitals occasionally, particularly when doing nucleophilic substitution reactions. When you are forming, let's say, a sigma bond between two s orbitals, let's see how we want to do this. We have a nuclei with an s orbital. We have another nuclei with an s orbital. We could just call this hydrogens. And when they're this far apart, they can't bond because they need to have the nuclei close enough where they can effectively share the electrons through space. And remember, a sigma bond is a linear bond where the electrons will share linearly through space between the two nuclei. And there can be a little bit of divergence from that. Sometimes it'll be a little off-center up here or up here, but most of the time it's going to be spending its time being shared between the two nuclei. If we start to move these two together, actually that's like an apart sign. If we move them towards one another, the potential to share electrons improves. And let's see if I can draw this. And when we get that ability to overlap, it looks something like this. So if we were looking at this on an energy scale, this is going to be, does that draw? Okay, it does. This is going to be, remember, higher up is high energy. High energy means less stable. Cool. Meaning looking for a chemical solution which will provide a lower stable or a lower energy, more stable configuration. So prone to react, right? So we're up here, and then we're at our low energy, more stable solution here. But what happens? Ooh, I've got this all. I drew this backwards. Sorry, guys. No, this could work. I'm just going to do it backwards. Well, no, I've erased it.
Just draw it again. No problem.
Yeah, it'll be okay. If these get too close together, this is asymptotic though. As they reach a certain point where they're separated enough, it doesn't matter how far apart they are. It's right. So it doesn't matter if they're this far apart or this far apart, this far apart. They're just too far apart, and their effect on each other goes away. So they reach a limit of how high energy they are. If they get pressed together even more, I'm going to get kind of silly here. You actually start to get repulsive effects between the nuclei. The electrons start to get crowded. The non-bonding electrons start to crowd one another, and it becomes high energy again. So there's just this happy place where the two nuclei have the ability to share the electrons, giving them stability, but they're not so close together that the nuclei and non-bonding electrons aren't packed in too tightly. And this is what determines bond length, is that balance of those two factors in any particular bond. So whenever we are putting orbitals together to form bonds, the total number of orbitals needs to stay the same. So as drawn here, I have an orbital here and an orbital here. But here I have one orbital. So we've gone from 2 to 1 as drawn in this. And in molecular orbital theory, it's really important that we show that the electrons are going into this orbital, but when they combine, we get in another orbital, which is a higher energy orbital, which is the antibonding orbital. And we're going to look at that real fast. So let's say we've got some nuclei with its atomic orbital at this energy level, and we have another one of those. And they come into proximity to one another and they can share their orbitals. And that's going to cause the formation of a new lower energy orbital. Where the electrons are being shared between the two nuclei. And there's going to be a higher energy orbital where the electrons actually have a strong planar node, and they spend their electrons are getting pushed away from one another. And this is our bonding orbital, and this is our antibonding. And people kind of freak out when they hear antibonding because it's kind of like antimatter. It sounds science fictional. Like, when are we going to use this? Like an imaginary number. These things that get thrown out at you throughout your education. And you're like, what is this good for? What's important to think of, bonding orbitals are bonding because electrons are being shared between the nuclei, and that forms a bond. These orbital solutions can house electrons, but they're much higher in energy, so there has to be some rationale for an electron to be there. In addition to that, they cannot be shared between the nuclei. So there's going to be scenarios where we see electrons in antibonding orbitals. There's almost always going to be electrons in other bonding orbitals as well. It doesn't mean that the two nuclei are no longer attached to each other. They're probably attached to each other through these bonding scenarios, but they can also be housing some of these higher energy electrons in antibonding orbitals. And that's going to become important because at some point, if you have a reaction, and you have an electron go from one nuclei to another, where does that electron go? Can it go into an orbital that already has electrons? No. It needs to go someplace else first, initially, as part of the transition state. Because remember, we have these beginning transition state, which is high energy product. These high energy zones often involve putting electrons into these higher energy orbitals so that you can have a structural rearrangement as you kick off something else, making room for those electrons to go into a bonding scenario. So don't be afraid of antibonding orbitals. They're actually super handy for explanatory power. Yes?
So is that just the same as an activation energy curve?
This?
Yes.
This is the energy of activation. There's lots of other, you can abstract a lot of other information from this as well, other than just activation energy. In 100 level, I refer to this, actually this is great because people actually knew the Greek story of Sisyphus in my 100 level class, right? So you've got Sisyphus, who was cursed by the gods to push a heavy stone up a hill only for it to fall, roll back down for eternity over and over and over again. And that's kind of just my display of potential energy. Well, we'll go down this path again, but if you have enough energy in your environment to push a system to here, it always has the opportunity to go one of two ways. It can go back to where it started, or it can go this way to a more stable product. And that's the premise of what equilibrium is driven by, because it's reversible. The difference is, in a favorable process where your product is in lower energy, it takes substantially more energy to push it back up this side than it does this side. So if it chooses this path back down as part of equilibrium, probabilistically, it's going to be pushed back up again and then reach its lower energy state and be less prone to get pushed back this way. But I digress. And I think that's all we need to do. No, it's not all we need for molecular orbital theory. We need to look at what happens with pi electrons too. These are only sigma electrons forming sigma bonds. What happens for pi? Pi. For a pi system, same thing. Let's see how we're going to do this. We've got pi electrons. We're going to orient them in the same way so they have the ability to share. And when we get them close enough to form, they share. These are nonlinear between the nuclei because the first bond's always a sigma bond, and that space between the nuclei are now occupied. So to form a second bond and a third bond, we have to go around the sigma bond. So these p orbitals will share electrons around the nuclei because this space between is already inherently occupied by a sigma bond. This is the bonding pi bond. The antibonding version of this still has nodes, but they're pushed away from one another even more so than they are linear. They are out of phase, and these electrons cannot be shared. If you house an electron in this high energy orbital, they cannot be shared between the nuclei. So it's the same premise as a sigma bond. That's bonding or antibonding, same rationale, just slightly different three-dimensional orientation in terms of the solution. Any questions about MO? This is as far as we're going to go for now. We'll go further later. Yeah.
I've seen in the book examples of the p orbitals in this instance connecting like end to end versus side to side. When does that happen?
We will be getting there before the end of class.
Okay.
We're gonna, yeah. So, good question, but we're definitely gonna get there. Any other questions? Whoa! Wait. You mean p orbitals connecting like that?
Not a thing. Okay.
If you got a picture in the book, pull it up for me here.
I'll look for it.
Okay.
I feel like I've seen things like this.
Okay. Now I'm super curious. I'm wondering what they're throwing in this book. Yes,
That's a sigma bond, though, isn't it?
that's a sigma bond,
Okay.
and it's a hybrid orbital, not a p orbital.
Okay.
Yeah, we're going to get there. Don't worry, we're going to spend some time. When we do hybridization, it'll make more sense. You're probably looking at an sp3 hybrid orbital bonding
Okay,
to an s
yep.
orbital.
That's what I'm looking
Okay, I know these. And here's an important difference. If we were looking at the bonding in the nodes of an sp orbital versus a p orbital is symmetric around the nucleus. An sp orbital is asymmetric.
Right. Okay.
And this will be the bonding zone for that interaction. Okay, so we're going to start with single bonds and hybridization, and then we're going to single bonds. Do I talk about hybridization explicitly, or let's see here? Okay, we're going to talk about hybridization. Single bonds, double bonds, triple bonds. So, first case scenario, hybridization with single bonds. And whenever you're forming your first bond, it's always going to be a single bond, which is a sigma bond. Second bond, third bond will be pi bonds, but the first bond's always going to be sigma bond because it's your strongest, most efficient path to share an electron between nuclei. So, our probably good way to look at this is just look at methane. So methane is one of our most simple organic compounds. CH4, 1 carbon, 4 protons. And if we draw this three-dimensionally, we'll see that it has a tetrahedral geometry. So if ignoring the 1s orbital because it's full, we're just going to look at the level 2 orbitals. How many valence electrons are in carbon? 4. So we're going to fill up the s orbital first. Positive spin first, and then positive spin, positive spin. So this is what the atomic orbital of carbon looks like. Now, under a high energy condition, so under high energy conditions, one of these electrons can promote. because here's the weird rationale for hybridization. I want to make sure I don't jump the gun on this. Right. If we were to predict bonds based on the way atomic orbitals look, we would have 2 electrons which are paired inside the s orbital, and we would have 1 electron in one of the p orbitals and 1 electron in one of the other p orbitals, and then the last p orbital would have no electrons. So if you were to form bonds with this, could you form a bond with that s orbital? Because it's full, right? So you can't put more than 2 electrons in the orbital, so you can't share. I mean, hypothetically, maybe if you had a proton that had no electrons and all the electrons were coming from here, maybe. Maybe. But it doesn't happen like this anyway, so I'm not going to try to guess any further. What's the angle between these 2 bonds, or these 2 orbitals, suborbitals? 90 degrees. Oops. We also know that all 4 of these bonds are identical in length and orientation. S orbitals are lower in energy and more closely held, and therefore form slightly stronger bonds than p orbitals. So if we had 2 bonds forming to the s orbital and 2 bonds forming to the p orbital, they would not be of equal length and strength. So we have a bunch of evidence that shows that this bonding of carbon to 4 hydrogens does not take place through atomic orbitals, because the angles are wrong, and the fact that all of the bonds are identical would not happen here. So under a bonding scenario, one of these electrons promotes. And this is, I'm going to throw this out here. A lot of books don't even show this step as part of hybridization, because it's super, super, super high energy, transient, but I think it helps. I kind of like it because it helps you see why the electrons are separating. Now we have 4 bonding possible electrons, but the same issue holds true. Even if I were to form a bond to S and I formed bonds to these 3 p's, I'd have 90-degree angles between all these p orbitals. And that's, by Vesper theory, just ridiculous, because they'd be way too crowded. So what actually happens is, during the bonding process, remember, an atomic orbital is just a solution of a wave equation which provides the lowest energy for sequentially adding electrons around a nucleus. Well, now we're sharing electrons between 2 nuclei, and those solutions of those same equations are substantially more complex, and they provide different solutions than atomic orbitals provide. In other words, this is the best low energy solution when there's 1 nuclei. When there's 2 nuclei, the orbitals change. And that's what hybrid orbitals are. So the s and all 3 p orbitals in this combine to form, so there's 1s and 3p, so a total of 4 orbitals will combine to form 4 new orbitals, which are all equivalent, which are sp3 orbitals, right? Which contains the s and all 3 p orbitals. 1, 2, 3, 4 equivalent sp3 orbitals. Let me drink. I can just get rid of this, guys. Don't need it. Let's see here if I can make sense of this. And each of them will house a single electron. So now we have 4 equivalent orbitals. And these orbitals look like this. In plane, out of plane towards you, away from you, out of plane. Tetrahedral. Vesper theory. You want as much room three-dimensionally around them as possible. There's also small nodes because each of these sp orbitals actually looks like this. Behind each of these, there's a small node of the orbital also, but it's rarely drawn. And you don't have to draw it. Now, in terms of energy level, sp3 orbitals, and this is not going to be perfectly to scale, are going to be lower energy than the p orbitals and higher energy than the s orbital because it's a combination of the two. These are going to be 25% S character, 75% P character because averages. Now the neat thing about it is if you were to sum the energy level of this plus this plus this plus this versus 4 times this, this would be slightly net lower energy than the sum of these. That's why it happens, because net, it's a lower energy solution between two nuclei than that. So now that we have hybrid orbitals, we can do bonds. That makes sense. And in the case of methane, I can use this. The carbon hybridizes, but the S doesn't. Doesn't need to. So we'll have an S to sp3 orbital sigma bond. And we'll have 4 of those. So this is hybrid orbital theory's explanatory power for why bonds form, well, single bonds, at least in the case of methane. Now, for ethane, ethane is just a pair of carbons that are saturated with 3 hydrogens apiece. It's very similar, except the bond between the 2 carbons, both carbons hybridize, forming 4 sp3 orbitals. That's probably what you were looking at. And then, let's see here, just want to do this. These lines are also hybrid orbitals, but it gets a little odd for me to draw them because it's hard for me to do spatial hybrid orbitals. So each of these would look like that. And then each of those ends will have a hydrogen which just has an s orbital binding to the sp3 hybrid orbitals. So this sigma bond is going to be sp3 to sp3, and these sigma bonds are all sp3 to s. Any questions so far? Oh, that's a bad sign. Either everyone absolutely gets it, or everyone's just kind of screaming internally.
and I understand it a lot better than it was taught in the 100 levels.
Cool. With a little practice, it'll get easier and easier and easier. And we're going to do some shortcuts at the end of this that make identifying them a lot faster. Because there's all kinds of shortcuts. For instance, oh no, I'll save it. Gotta save the shortcut for the end. Can't teach the shortcut first. Yes. Now that I erased it.
Sorry.
It's okay.
What about double bonds?
That's what I'm about to do. I'll pay you later for the prompt. No, the best unprompted question from a student is I was being reviewed before getting tenure by somebody who's the director of biology. And so she comes into class, and it's OChem, and somebody just like, can I ask a question about the homework before we get started? I'm like, absolutely. And then I knew the answer, which is even better. And it was a great way to start the class, and she thought that was like our routine. But it just happened that somebody had a question, so it's like, oh man, this is really opportune. But what am I looking at here? Okay, double bonds. So a double bond has two bonds. The first bond is a sigma bond. The second bond is a pi bond. And when there's a criteria for this that's really important. Whenever you have a bonding solution which involves single bond, it's going to become sp3. When you have to form a double bond to adequately share electrons between nuclei so everything has an octet, you need to have a way to share those electrons around the sigma bond. So a sigma bond is going to, so what's going to happen is we still only have our two s electrons and our two p electrons. We still only have 4 electrons. So if we're going to share 2 of those electrons between a nucleus, we have to have a way to get around the sigma bond. And that means we can't hybridize one of these orbitals. Whereas before, we hybridized the s and all 3 p orbitals. When we do a double bond, we only hybridize 2 of the p orbitals, and we leave one of the p orbitals unhybridized. So what ends up happening is we get 1, 2, 3 sp2 hybrids and 1 unaffected p orbital. And when we fill this, each of these gets an electron for bonding. So, whereas sp3 is s1, 2, 3p, 4 hybridized orbitals, this will only have 3 hybridized orbitals and the p orbital. And what that looks like is a trigonal planar setup with the hybrid orbitals and a 90-degree orientation of the p orbital to that. So let's see if I can draw this in plane. So there's our 3 sp2 orbitals, and then we've got our p orbital. This is the hybridization that's going to take place to form a double bond. And I'll show you why here. Let's do ethane. Ethene, excuse me. notice, as drawn, approximately 120 degrees between all bonds, and planar. What's going to happen is the first bond is going to form by linearly sharing the pair of electrons between the two nuclei, giving us our sigma bond. And then the second bond forms around that sigma bond by sharing electrons through space in this one plane. And this is really important because, and we're going to talk about this later, but I have to just make it relevant right out the gate. This bond between this carbon and these two carbons has freedom of rotation. I can take these and spin them, and they're not all equal in energy, but there's no really strong chemical rationale for why we can't move it through that range of motion. I can just take these and spin them around this like it's got a joint between them, because there's no reason it can't. It can still share the electrons regardless of the orientation of the other groups. With a pi bond adds rigidity. For these electrons to share, these p orbitals have to be aligned. I can't share electrons through space diagonally like this. They have to be aligned just right, within just a tiny margin of each other to share those electrons. So the p orbitals can share through space, but they have to be aligned just right to do so. And this explains why this system has 120 degree bond angles that are planar. And if we wanted to go further out to the hydrogens, we could say that this is an sp2 to s sigma, this is sp2 to sp2, and this is a p to p pi. So y'all can break that down pretty straightforward once you get there. And the natural question is what about triple bonds? Oh, remember, because we only have 3 sp2s, this now has 33% S character and is 67% P character. Meaning sp2 bonds have more S character than sp3s. Which orbital is lower in energy, S or P? So, which hybrid orbitals are going to be net lower in energy, sp2 or sp3? sp2, meaning they are inherently going to be more stable / stronger. Right. In the absence of other effects. So for we'll just do this. Triple bond. Triple bonds have 3 bonds, and the first one's always sigma, and then both of the other ones are pi. We now have an intuition that the second pi bond also has to come from a pair of non-hybridized p orbitals, which means in this solution, when we have to share 3 pairs of electrons to get an octet, the hybrid orbital solution requires hybridization of only 2 orbitals to be lowest in energy. So whereas we have 1, 2, 3, 2 p orbitals, a low energy 2s orbital, unhybridized, when they hybridize, I'm trying to get these lower in energy. Ooh. SP. Because there's only these two orbitals hybridizing, and then these two orbitals just move over without being altered in energy. And we're still going to distribute the electrons. Whoa. No, look, that's nitrogen I just drew. 1 electron apiece. If we're going to do that exact same rationale, now there's only 2. Let's see here. We're going to have, if you only have 2 orbitals, how are they oriented in space as far apart from each other as possible? What's that called? Linear. So we're going to have one of them here and one of them here. So this is going to be, the first bond is going to be sigma bond, and it's going to be sp to sp hybridized. And then our second bond is going to be through space and aligned, and then our through a p, and then the other vacant p orbital, which houses an electron, is going to share space 90 degrees away. So we've effectively, in all dimensions, surrounded the sigma bond with electrons in the form of pi bonds. And that just leaves us 1 electron apiece here, because this compound only has 1 hydrogen per carbon, and this is going to be an sp sigma. Then obviously sp pi, sp, or excuse me, p to p pi, p to p pi. And this drawing obviously gets a little bit, hopefully the colors help a little bit, but the picture in the book's pretty good also, so to get any kind of extra clarity.
Which ones of that are the pi bonds?
The nonlinear. So the sigma is always the one that is shared directly between the nuclei, and anything that is happening around that sigma bond is going to be your pi bond, and it's also going to be the one that involves the non-hybridized p orbitals, always.
So pi bonds are always
PP. P to P.
and which one is the SP?
The sigma bond, the first one that forms linearly between the nuclei. The blue one. For those who aren't red-green colorblind doesn't apply here. I had a professor who was super colorblind, and anytime you used any color in any visual presentation, he freaked. So you had to do everything in black and white to appease him. I had a question over here somewhere. Yeah.
Yeah, so the carbon and hydrogen bond and an sp hybridized carbon, would that be a stronger bond than sp2 hybridized carbon?
Yes, because it has 50% S character and 50% P character. Without any other effects, other variables impacting it. Yeah. As we get a little bit gnarlier with this class, we're going to start throwing other variables, which can totally change that assumption. But for now, we'll just roll with it. Okay. Any other questions before we keep chugging along? Yes.
Just go through which orbitals are which again in that drawing.
This one?
No.
This one?
Yeah.
Ugh. No. Okay. So the first bond is going to be formed through the hybrid orbitals, which is linear. And there's two hybrid orbitals that are rotated 180 degrees away from each other because of Vesper rules. So we're going to share those two electrons in this first sigma bond, and then we'll have an unoccupied or non-bonded electron here. So we had, this is, for each carbon we have two sp. So this is carbon 1, this is carbon 2. This is the first pair of sps combining, and then we have an sp over here and an sp over here. And then each of these has a pair of non-hybridized p orbitals, each of which has an electron, and then they can share across that sigma bond with a pair of pi bonds. Any other questions? Ready for shortcuts? Everyone loves shortcuts. Tell me I'm recording. Oh, good, I'm recording. I was like, I had a panic attack. Let's see here. So you can often, or well, you can tell what the hybridization is based on geometry, right? At this point, you can kind of intuit that. If something is tetrahedral, it's sp3. Now, caveats. By tetrahedral, I mean counting all of the electrical groups. Multiple bonds count as a group. Lone pairs count as a group. So, methane is tetrahedral electrically and is sp3. Ammonia is tetrahedral electrically and is sp3. Water is tetrahedral electrically and is sp3. If something is trigonal planar, it's sp2. Meaning, instead of 109.5, we're looking for those 120-ish degree angles. Of course, this has more electrical density here, so this will be slightly more than 120. The bonds between the two protons will be slightly compressed, but ballpark 120. If it is linear, we're looking at sp. Another modification / shortcut is you can look at this and say, if it's all single bonds, it's going to be sp3. If it has a double bond, or let me rephrase that, if it has two bonds to the carbon, it's sp2. If it has three bonds to the carbon, or excuse me, four bonds to the carbon, they all have 4 bonds. One double bond, one pi bond. We're going to go with pi bonds. One pi bond, it's going to be sp2. 2 pi bonds means sp. So this has a single sp to sp sigma bond, and it has 2 p to p pi bonds. A good example, and the reason I'm going to this clarification, is because if you look at CO2, it's linear. That is sp. Also, and it has 2 pi bonds also. It just happens to have a pair of sigma bonds also. So, yeah.
SP bond, a pi bond, or a sigma bond?
That's the sigma bond. Ooh! Thank you. It's a sigma bond. Good catch. So, you're going to get a real fast feel by looking at geometry and looking at number of pi bonds, what the hybridization should be. And there's one little trick to this, and we're going to get into it in the acids chapter a little bit, but I want to throw this curveball at you now because it's really important. If anything, who here remembers resonance? A little bit about resonance. We got some familiarity with resonance. Okay. We're going to do a lot of resonance, don't worry. We're going to get better at it. If anything has, because of resonance, any double bond character, any significant double bond character, that has the potential to behave as a double bond as part of a resonance structure, to do so, it has to have an available p orbital to house those electrons, which means it has to be hybridized as sp2, not sp3. So an example, we have a carboxylate ion, which is carboxylic acid, which has lost its proton. One of the oxygens is housing an electric charge. It turns out that these oxygens are actually identical because of resonance. R is just a holding place for anything else that might be attached over here. We're not paying attention to it. It's insignificant, so I just throw it on as an R group. These electrons can very easily, that extra pair which houses that charge, causes that charge, can move between the carbon and oxygen as bonding. That exceeds the number of available bonding positions on the carbon because we already have 1, 2, 3, 4 bonds. So if I were to put another one on that, that would have 5 bonds. But when we do this, it pushes these electrons up here, giving us a resonance structure. It looks like that. This oxygen is just as capable of holding the charge as this oxygen. So we have a 50-50 distribution of resonance, of holding the electrons. Sometimes resonance structures aren't perfectly equal. This one is. If I were to ask you on an exam, what is the hybridization on that oxygen? And what's the hybridization on that oxygen? Your gut reaction after this last part of the lecture would be, well, that has to be sp2 because it has a double bond and its electrical groups are trigonal planar, and this one's got 4 electrical groups and it's tetrahedral and has a single bond, so this has to be sp3. But you'd be wrong because this has double bond character as well because of that. And to hold those electrons as a pi bond, it has to have a vacant p orbital. So you can't hybridize all of its orbitals. So this is sp2, and this is sp2, and this is sp2, and this is sp2. None of those oxygens are sp3.
So the rule is that resonance for a double bond.
If via resonance, if it has any double bond character as part of a good resonance structure. We'll talk about good versus bad resonance structures later. So just keeping it. Now, don't confuse that with a carboxylic acid because there's no resonance there. Because I can't push those electrons off equally. But don't worry, we're gonna flesh that out later, but I just wanted to throw that caveat into this mix before we went any further. Before we move on, yeah.
Is there also a rule for that for resonance for triple bonds and SP?
With triple bonds, you're never going to see a resonance where triple bond goes to a single bond, so it's always going to have vacant hybrids. Vacant p orbitals. I shouldn't say never, but it's not going to happen in the next semester or this semester.
So in that case, right, so for just the oxygens or SP hybridized, they're the ones that have the resonance double bond.
Yes. And the carbon what's the hybridization on the carbon? Because it's got a double bond and it's trigonal planar. And that doesn't change regardless of where the double bond's located. So some generalities. A stronger bond is a shorter bond, right? Because what determines bond strength? The degree of electron sharing, how much those orbitals overlap. So generally, a single bond is not as strong as a double bond, which is not as strong as a triple bond. Now the important thing is that the double bond is not twice as strong as the single bond, because this is a sigma bond, which is the best way to share electrons efficiently between nuclei. And this pi bond is not as strong because it's sharing electrons less efficiently peripherally around that sigma bond. So it's stronger and therefore shorter, and the nuclei is closer to one another, but it's not twice as strong or twice the length. And here we have a sigma and a pair of pi, and it is, once again, stronger and shorter, but not 3 times as strong as a single bond. Now, along those same lines, we're talking about things where every other variable around these questions are very similar. We have sp hybrids, sp2 hybrids, and sp3 hybrids. Which bond would be stronger, an sp to s or an sp3 to s? Right, because it has more s character. Therefore, this is a lower energy orbital to an s, which is lower in still. So, going to be stronger. What about sp3 to sp3 versus sp3 to s? You guys are great. You got it. Last thing this chapter covers was net dipoles. Dang it, I'm not going to make it to acid spaces today. It's okay. We're going to let me just talk about the conventions of how we show dipoles so that what I do on the board makes sense. So for any bond where you have a difference in electronegativity between the two nuclei, the electrons are going to bias towards the nuclei which is more electronegative. And an easy example is hydrochloric acid. So hydrochloric acid, the chlorine is vastly more electronegative than the hydrogen. So although we are sharing electrons between the two nuclei, it's like a 5-year-old sharing with a 1-year-old. It's like, yeah, 1 for you, 1 for me, 2 for you, 2 electrons for me. So instead of being shared like this, it's more like this, where the electrons are owned around the chlorine more often than the proton. Now, because of this, you're going to get a partial positive charge on the proton and a partial negative charge on the chlorine. and we draw this as a dipole within the bond as an arrow pointed towards the electrical density with a little cross on the back, which is a positive charge. So when I draw this, what it's showing is everyone's taken some kind of math that involves vectors or had physics with vectors. This is a vector. I don't know. Okay. Oh, shoot. Yeah. Okay. So I'm going to change my language then. This is an arrow which gives you an idea of the direction and magnitude of how the electrons are biasing in the bond. Now, the reason that's important is because even though bonds can be polar, how they're oriented three-dimensionally matter in terms of the net dipole for any molecule. So a great example is carbon tetrachloride. So carbon tetrachloride, 1 carbon, 4 chlorines, any particular carbon-chlorine bond is going to look like this. And if I were to draw this out three-dimensionally, each one of these bonds has a dipole of equal magnitude pointing away from each other at 109.5 degrees. Now, the thing is because all these bonds are equivalent and all the angles are 109.5 degrees, all of these cancel each other out. So if you think of this as in somebody playing, so if you're playing tug of war, let's say this is a trigonal planar tug of war, and you were pulling with equal force in all directions, and you had a locator in the middle at that joint wouldn't move. If I pulled harder this way, it would move because net, the electrons, or the force would pull this way. But if all the forces are equal, that doesn't go. In 3 dimensions with a tetrahedral arrangement, the exact same thing happens. You can pull the electrons in all directions equally, and so even though each of these bonds has a dipole, the net dipole for the molecule is 0. This is not a polar compound, even though it has polar bonds. Ammonia has 3 equivalent bonds. The nitrogen's more electronegative than the hydrogen. But the presence of the lone pair is highly electronegative. And if this was tug of war and everything was pushing this way, you'd get a net dipole for ammonia. So ammonia is a polar compound which contains some polar bonds. Another good example of a symmetric compound which has polar bonds that's not polar. Carbon dioxide. It's linear, has dipoles like this. They're equal. They're 180 degrees apart. It's just a perfect example of tug of war. No net dipole. So just because something has polar bonds doesn't mean the entire compound is polar. So keep that in mind when we're addressing those questions. And we'll pick up on Wednesday because Monday's a holiday. I know. I got to keep this mojo rolling. We'll do acids and bases. Have fun.
Open up each week's homework after the previous week's been completed.